Hello, math students. Systems of linear equations. Now, the following table summarizes linear equations in both 2- and 3-dimensional contexts. The linear equation ax plus by is equal to c, where x and y are the variables and a, b, and c are constants, represents a 2-dimensional equation, and when you graph it, it's going to produce a line in the xy plane. Now, one comment we should make is that a and b are not both 0, but it is possible for one of them to be 0. Now, if we introduce a new variable, z, we have a linear equation of this form, ax plus by plus cz is equal to d. This represents a 3rd-dimension equation, and the shape of it is going to be a plane in the xyz space. And the only comment is that we can't have all 3 of them be 0. Now, a system of linear equations is a collection of linear equations. The solution to a system is the set of all points that simultaneously satisfy all equations in the system. And a system with at least one solution is called consistent, and a system with no solution is called inconsistent. Determine whether each point below is a solution to the accompanying system. Traditionally, when you see an ordered pair, we think of the first one as x and the second one as y. And determine whether this point satisfies this system of 2 equations, we just have to verify that it satisfies both equations at the same time. So let's check equation 1. If you plug in 5 for x, so you have 2 times 5, at the same time that you plug in 3 for y, the question is, what does this produce? And we get 10 minus 3, we get 7, so equation 1 is satisfied. Now let's check equation 2. If you plug in 5 for x, so we have 5 minus 3 times, and then plug in 3 for y, we get 5 minus 9, that's negative 4. Negative 4 is not 6. The point does not satisfy the second equation, therefore it's not a solution. 5, 3, not a solution. That doesn't mean that the system isn't consistent, it just means that this point isn't a solution. Now in the 3-dimensional context, let's go with the convention that the first one's x, the second one's y, and the last one is z. Notice I cross my z's just so they don't look like 2's. I recommend you might do something similar. And let's check all 3 equations. Equation 1, plug in 2 for x, so we have 2 times 2, minus plug in negative 1 for y, and then plus, and then plug in 4 for z. And the question is this going to give us 9? So you have 4 minus negative 1, so that's 4 plus 1, that's 5. Add 4 is 9, so check. Let's try equation 2. Oh, notice there is no x to plug in. 4 is z minus 3 times y, and y is negative 1. So we get 4 plus 3. That does give us 7. Second equation is satisfied. Let's see if the third one is. So 3 times x is 2, plus z is 4, minus 2 times y is negative 1. So we get 6 plus 4 is 10, plus 2, that does give me 12. And so we have satisfying all 3 equations at the same time. Thus, the point 2, negative 1, 4 is a solution. Okay, we're going to now focus on how to find solutions, and we're going to begin with the 2-dimensional, 2-variable context. One way to solve a system of equations is to use methods of substitution and or elimination. Solve the system below using substitution and elimination in various ways. Then graph each equation in the system and interpret your answer. And the substitution approach is to take either equation 1 or equation 2 and solve it for either x or for y, and then substitute that expression into the other equation. So this gives you 4 different ways you can begin this. I'll demonstrate 2 of them. I'm going to take equation 1 and solve it for y. I could solve it for x, but I'm going to choose y because y has a plus or minus 1 in front of it, so I don't need to create any fractions. If I tried to solve this equation for x, I would have to divide everything by 2, and that would cause some fractions. And fractions tend to slow down the process and or lead to silly mistakes. So let's take that equation and solve it for y. So I'm going to take this y and add it to the right side and take the 7 and put it on the left side so that it looks like 2x minus 7 is equal to y. And then substitute that into equation 2. Equation 2 reads x minus 3 times y, and y is 2x minus 7, use parentheses here, is equal to 6. Now we distribute the negative 3, so we have x minus 6x plus 21 is equal to 6. Combine the x's, negative 5x, subtract the 21 from both sides, gives me negative 15 over there, and then divide by negative 5, and we get x equals 3. Now once you know x, you can substitute x into either of these equations and solve for y, or even this equation here. This seems like the best one to plug x into because y is already isolated. So we know that y, therefore, will be equal to 2x minus 7, and x is 3. So that gives me 6 minus 7, which is negative 1. So our answer is 3, negative 1. Now, I'm going to do this a different way, using substitution still, but I'm going to take equation 2. And because x is all alone, I'm going to just isolate the x even further. So we're going to get x is equal to 6 plus 3y. So equation 2 tells us that x is equal to 6 plus 3y. I'm going to substitute this into equation 1. Notice how I'm referencing my equations. This is a helpful practice, especially when we get more and more equations to keep track of. So equation 1 is 2x, and 2x is the same thing as 6 plus 3y, and then minus y is equal to 7. Distribute the 2, we get 12 plus 6y minus y is equal to 7. 6y minus y is 5y, and subtract 12 from both sides is negative 5, and we get y equals negative 1. Notice I get y first this time. I'm going to go into this equation right here and plug in y equals negative 1. So we get x is equal to 6 plus 3 times negative 1. That's going to be 6 minus 3, which gives me x is equal to 3. So 3 negative 1 is confirmed using a different way of substitution. Now, elimination methods are methods where you adjust one or both of these equations so that when added together, one of the variables will cancel. Notice if I added the equations together now, I'd get 3x and negative 4y, and then equals 13. That statement I just read still has x and y. What I want to do is adjust one of the two equations, or maybe both, so that when added together, either x or y cancel. And again, there's lots of ways to do this. I'm going to target the x's to cancel. So I'm going to put a negative 2 in front of this x right here. So I'm going to multiply this equation, both sides of it, by negative 2. So we have negative 2 times equation 2. And this gives us negative 2x plus 6y equals negative 12. And then I'm just going to rewrite equation 1. No need to adjust it. That's 2x minus y is equal to 7. And now we're in a position where if I add the two equations together, we will get cancellation of the x's. 6y minus y is 5y, and negative 12 plus 7 is negative 5. And that gives me y equals negative 1. And then we do the same thing we did before. Substitute negative 1 into either equation, solve for x, you get x equals 3. We could have also targeted the y's for elimination. So if this was a plus 3 in front of this y, and this is a minus 3y, then when added together, they would cancel. So I want this to be a plus 3, which means I need to multiply all of equation 1 by negative 3. Negative 3 times equation 1, we get negative 6x plus 3y is equal to negative 21. And then the second equation, I don't need to change. Equation 2, we'll leave it as x minus 3y is equal to 6. Add the two equations together. We get negative 6x plus x is going to be negative 5x. The y's do cancel, and negative 21 plus 6 is negative 15. And then divide both sides by negative 5, we get x equals 3. Plug x equals 3 into either equation, solve for y, you'll get negative 1. Now personally, between these two methods, I do prefer using elimination strategies as much as possible. But there are times where substitution seems very convenient as well. Now what we're supposed to do next is graph the two lines. So I'm going to take equation 1 and solve it for y. So equation 1, when solved for y, is y is equal to 2x minus 7. The reason I'm doing that is I'm just putting it into y equals mx plus b form. I know that negative 7 is a y-intercept, and the slope is 2. So I'm going to make a line that has slope 2. What I was looking at when I did this was a run of 1 and a rise of 2. So I wanted to make sure I went through that point as well. So there's that first equation. Solve equation 2 for y. Subtract 6 from both sides. So we have x minus 6 is equal to 3y. Therefore divide, we get minus 2. And the slope is 1/3. So that means if I do a run of 3, I should do a rise of 1 to get to another point. Okay, and then our solution, of course, is the point of intersection. This is the point that satisfies both the red and the green equations. You might be able to surmise then, if you have two lines with different slopes, there will always be a point of intersection somewhere. Solve the system below using both substitution and elimination. I like the fact that I can take equation 1 and just solve it easily for y, so I'm going to do that. I'm going to add y to one side, subtract 4 to the other side. So equation 1 yields that y is equal to 2x minus 4. And I'm going to plug that into equation 2. So we have negative x plus 1/2 times y, and y is 2x minus 4, and this should be equal to negative 2. And we'll solve this for x. Distribute the 1/2, so we get negative x plus x minus 2 is equal to minus 2. And the x's cancel, notice, and we have minus 2 equals minus 2. This is a true statement. It's always true. It doesn't seem to matter what x is, which is interesting. What does this mean about our solution? Let's try elimination. If I were to try to eliminate the x's, then I would want to double equation 2. Doubling equation 2 gives me negative 2x plus y equals negative 4. And then equation 1 was 2x minus y is equal to positive 4. And when you add these equations together, keep in mind my goal was to cancel the x's, but notice that the y's also cancel. We get 0 on one side and 0 on the other side. So these might be confusing findings. What did this mean about our solution? Well, let's go ahead and graph them. Equation 1, solving for y, which we already did, is y is equal to 2x minus 4. So that's going to have a y-intercept of negative 4 and a slope of 2 again. And equation 2, solve that equation for y. I'm going to add the x to the other side and then double everything. So we get y is equal to 2x minus 4. Oh, that's interesting. Turns out that it's the same line, which means every single point on the line is a point of intersection. That suggests that there are infinitely many solutions, but we still want to describe what they are. They're not just any point. Like this point over here is not a solution. It has to be a point on the line. So our solution is all points on y equals 2x minus 4. Sometimes your solution is written this way. X could be anything, but then y has to be 2x minus 4. So all points of this form the solution. When you get these kinds of trivially true statements, that's probably an indication that there's going to be some overlap of lines or planes or whatever the shapes are that are involved. And the best way in the case of two dimensions to verify that fact is to put them both into y equals mx plus b form. If they wind up being the exact same expression, that confirms that they are in fact the same line. Okay, let's go to the next slide. Solve the system below using both substitution and elimination. Then graph each equation in the system and interpret your answer. Okay, so for substitution method, clearly I'm going to just solve this one for x. So equation 1 yields that x is equal to negative 2y minus 4. And then substitute that into equation 2. We have negative 3 times x, and x is replaced with negative 2y minus 4. Then we have minus 6y, and is equal to 18. Distribute the minus 3, gives us 6y plus 12 minus 6y is equal to 18. The y's cancel, leaving a statement that's 12 is equal to 18. Now this is a false statement, and that might be a confusing result to have, and what does that mean? Well, let's try elimination and see what happens. To eliminate, I'm going to target the x's for elimination, so I'm going to triple the first equation. That gives me 3x plus 6y is equal to negative 12. Don't forget to triple both sides. Equation 2 I'm going to leave untouched, and then add the two equations together. Now keep in mind I did set this up so that the x's would cancel, but also the y's cancel, but this side does not. So we wind up with a statement that reads 0 is equal to 6. Again, this is also a false statement. Okay, how to interpret these dead ends? Equation 1, I'm going to solve it for y. We get 2y is equal to negative x minus 4, then divide everything by 2, so we get y is equal to negative 1/2 x minus 2. So we have negative 2 and a slope of negative 1/2, so if we go over 2, and then we would go down 1 to get to another point. Equation 2, if we were to solve equation 2 for y and see what it looks like, I would add 6y to this side and then subtract the 18 to that side, so then divide everything by 6, and that would give me y is equal to negative 1/2 x minus 3. So this is going to be the exact same line, the same slope I should say, but a different y-intercept. So it goes through negative 3 instead of negative 2. And the two lines are parallel, but not the same. Same slope, but different y-intercepts. And when two lines are parallel, they will never have a point of intersection. So we say that this system has no solution. That means it's an inconsistent system. This will be the case whenever in the process of substitution and or elimination, you wind up with some false statement. Okay, the next slide. Now, given a system of linear equations, there can only be one of three cases regarding the solutions. Fill in the missing entries of the table below with an illustrative drawing. Now, there's already illustrative drawings for the three-dimensional case, but not for the two-dimensional case. One possibility with a system of linear equations is that there's no solution. And in the case of two dimensions, that just would mean that we have parallel lines. So this is equation 1, this is equation 2. We have parallel lines. That's the only way that you have two equations and you have an inconsistent system. Now, in three dimensions, all sorts of things can happen. So let's say we have three equations and three variables, x, y, z. Each of those equations that are linear would be a plane. Now, to be a solution to that entire system, we have to find points, x, y, z, that satisfy all three equations at the same time. In other words, we have to find all points that are on this plane, and on this plane. It has to be on all three planes. So there's lots of ways you can have inconsistent. Here's a situation where three planes are interacting in such a way that there are points of intersection, but there are no points of intersection for all three. The red, green, and blue don't have any points in common. Here's a case where green and blue are parallel planes, and red cuts through both of them. But again, yes, there are points of intersection, but there are no points of intersection for all three planes. Or you could just have three parallel planes like this, and there would be no points of intersection. I challenge you to come up with other ways that maybe planes might interact in such a way that there is no solution. Now, there could be only one solution. In the case of lines, it just means equations 1 and equations 2 have different slopes, and you would have a single point of intersection. In the case of planes, when this happens, you would expect you have three planes and they intersect at one point only. And then the other possibility is that you have two lines and they're the same line. So this is 1 and 2. And in the three-dimensional case, you could have infinitely many solutions in a variety of ways. Like in this case here, all three planes do intersect along a line. So you'd want to describe all those points of intersection somehow. Or what if you only have two equations and three variables though? So you would have just two planes. And two planes, they can have points of intersection all along some line. So you don't want to describe what that line is. Or what if you have three equations and they're all the same plane? This is what this is saying, 1, 2, and 3. They're all the same plane. So every single point on that plane would be a point of intersection. So these are all examples that yield infinitely many solutions. Now let's solve a system with three equations and three variables, x, y, and z. So notice that the first equation here has fractions. It's a lot easier to work with these equations if you eliminate all fractions to begin with. So the first thing I want to do is actually double the first equation. So we have now just x plus 2y plus 4z is equal to 15. And I'm going to shift my focus now to these three equations are the system I'm going to solve. Let's call this equation 1, equation 2, equation 3. Now I'm going to use elimination methods to get rid of some of the variables. Find any two equations and alter them in such a way so that when added together, one of the variables will cancel. So one of the things I notice is if I were to target canceling the x's, I could use equations 1 and 3 to do that. So I'm going to create a new equation, equation 4, and it's going to be found by adding equations 1 and 3. Adding negative x and x cancel, adding 3y and 2y is 5y, then adding negative z and 4z is 3z, and then finally adding 4 and 15 is 19. So this is equation 4, and notice it has no x's. Once you found a way to cancel x's by using two equations, then you want to make sure that you cancel x's again by using a different pair of equations. So just use equations 1 and 2 or equations 2 and 3. I'm going to use equations 1 and 2 to cancel the x's. I'm going to have to first multiply equation 1 by 5. So we're going to create equation 5 by doing 5 times equation 1 and adding that to equation 2. So we'll do a little bit of arithmetic in our head. So imagine multiplying this by 5 and then adding it to 5x and the x's cancel. Multiply this by 5 is 15y and add it to that negative y gives me 14y. Multiply this negative z by 5, so it's negative 5z, add it to 3z is negative 2z, and finally multiply 4 by 5 is 20, and add to 2 is 22. We created now a system of two equations with two unknowns, y and z, and I can go about solving them using substitution and or elimination still. I want to cancel the z's here, so I'm going to create a new equation, equation 6, by doubling equation 4. If you double equation 4, you get 10y plus 6z is equal to 38. And I'm going to triple equation 5 to create equation 7. So we get 42y, 3 times negative 2z is negative 6z, and then 3 times 22 is 66. Now these are perfectly set up so that I can add together. The z's will cancel so I can find y. So 10y plus 42y is 52y, and the other side of the equation, 38 plus 66 is 104. Fortunately, we wind up getting a whole number for y. This doesn't always happen. Sometimes you get fractions for your answers, but we get y equals 2. Now once you know that y is 2, I would substitute it into either equation 4 or 5. These only have y's and z's, and if you know y, you can then find z. So we're going to go back to equation 4, for example, and plug in y equals 2. So we have 5 times 2 plus 3z is equal to 19. You can see y across my z's, because that could easily look like a z. If that wasn't crossed, it might look like a 2. So we have 10 plus 3z is equal to 19. Subtract the 10 from both sides, so we have 3z is equal to 9. Therefore, z has to be 3. And then once you know z, you can substitute into any equation. Let's go back to equation 1 and substitute in what we know about y and z and solve for x. So equation 1 is negative x plus 3y, and y we discovered is 2, minus z, and z we discovered is 3, is equal to 4. So we get negative x plus 6 minus 3, so that's going to be plus 3 is equal to 4. Subtract 3 from both sides, we get negative x equals 1, therefore x has to be negative 1. And so our solution looks like we get a single point. Our solution is negative 1, comma, 2, comma, 3. And so we have this case right here. We have 3 planes that intersect at that single point. Now, when you're working with a system of 3 equations and 3 unknowns and you're using substitution elimination methods, if ever you produce a false statement, like suppose after some adding equations together you wind up saying that 0 equals 3. If that happened, then you would know that the system was inconsistent. So you would know that you would be up here somewhere in one of these kinds of cases, but you would certainly have an inconsistent system if ever you produce a falsehood. If you wind up producing a trivially true statement, like in the two-dimensional cases when we got these true statements, then that's an indication that there's probably infinitely many answers, and we have something like this. But what we're going to do is talk about in our next section a method for expressing answers when you have this bottom case, especially in 3 or higher dimension. Okay, let's go on to a couple applications. $378 is the revenue from selling tickets to Friday's school play. Students had to pay $2.50 each, and non-students had to pay $3.50 each. 120 tickets were sold. Find the number of students and the number of non-students who attended the play. I'm going to make a table, and in my table, I'm going to keep track of students, and we'll say non-students, and the price that they had to pay, the number of tickets, and then the revenue. So the price that students have to pay is $2.50 each, and price will be in dollars per ticket. And non-students had to pay $3.50. So now the number of tickets we don't know. We don't know how many. That's what we're trying to find. So let's say we sold X student tickets and Y non-student tickets. And the revenue we don't know, but we know the totals. So we know the total number of tickets was 120 and the total revenue was $378. But if you sold X tickets at $2.50 per ticket, then we know that the revenue would be 2.5 times X. And for the non-student tickets, it would be 3.5 times Y. And so this is going to allow us to create two different equations with variables X and Y. So our system looks like X plus Y have to equal 120 tickets. We'll call this the ticket equation. And then we have the money equation. We know that 2.5x plus 3.5y has to be 378. And this is the system that we would want to solve. Now I don't like the decimals. If I double equation 2, I can rewrite my system. Not only am I going to double equation 2, I'm going to do a little bit of foresight here. If I double this 2.5x, I'm going to get 5x. And I want to set up elimination, so I want that to be negative 5x. So I'm going to do a couple things here. I'm going to multiply equation 1 by negative 5, and that gives me negative 5x minus 5y is equal to, and 120 times negative 5 is negative 600. And I'm going to double equation 2 to get rid of the decimals. Doubling equation 2 gives me 5x plus 7y, and doubling 378 will give me 756. Now I've set up elimination of the x's, so I can add the two equations together. Negative 5y plus 7y is going to be 2y, and adding 756 and 600 gives me 156. And then solve for y, we get y equals 78. Now we know that 78 tickets were non-student tickets, therefore we know that the rest of the tickets had to be student tickets. And so this means that non-student tickets was 78, and the student tickets, we just do 120 minus 78, and that's going to give me 42. And this would be our solution to this word problem. Find the equation of the parabola, y equals ax squared plus bx plus c. So this means find a, b, and c essentially, which passes through the points and 3 points are given. Feel free to use technology to solve any system you create and to confirm your answer. So let's just focus on creating the system, and then I'm going to use something called Wolfram Alpha to solve the system. So whatever a, b, and c are, they have to be such that when you plug in these points, you get true statements. So if you plug in x equals negative 2, you want to get y equals 9. And so we're going to create equation 1 by changing the y to 9, change all the x's in here to negative 2. So negative 2 squared is going to be positive 4. So we're going to get 4a, bx, x is negative 2, so this will be minus 2b. Remember, we're changing x to negative 2. And then plus c, that doesn't get affected by the negative 2. And this has to yield a 9. Go through the second point, plug in 2 for x. That's going to give me 4a plus 2b plus c, and that is going to have to give us negative 3. And now we want to satisfy the third point, so plug in 6 for x. So plug a 6 into this expression for x. So we have 36a plus 6b plus c, and the result of this, the y-coordinate has to be 1. So here's our system, and I'm going to use Wolfram Alpha to solve this for a, b, and c. Don't get hung up on the fact that we have different variables. It doesn't matter. These don't have to be x, y's, and z's. To do this with Wolfram Alpha, in the input line, you just type in the word solve, and then type in your first equation, comma, your second equation, comma, and your third equation. Then you hit enter, and it should show you the interpretation. It should write the system down and make sure it looks right. And then it gives you the result, what a, b, and c are. So a is 1/2, b is negative 3, and c is 1. And this is our solution. So the parabola that we're after is y is equal to 1/2 of x squared minus 3x plus 1. This is the parabola that will contain all 3 points. And let's confirm that using technology as well. In Desmos here, I plotted the 3 points. I used a table to make the 3 points. And then I typed in the parabola, and I'm going to reveal it now. And sure enough, it winds up being the correct parabola that passes through all 3 points. All right, that wraps up our lecture.